building blocks of the universe turned out to be, well, made of something even smaller, and frankly, quite a bit stranger.
Yeah, stranger is definitely the word for it sometimes.
Right. So today we're taking a deep dive into exactly that idea. We're exploring the incredible, often counterintuitive world of quarks.
It's a fascinating place, the quark world.
We're going to try and unpack their surprising discovery, understand how they sort of glue matter together, and maybe grapple a bit with the profound mysteries they still present.
Still lots of mysteries, absolutely.
Our mission here is to give you a clear, engaging, hopefully comprehensive understanding of quarks. We've gathered our sources, and we want to offer you a real shortcut to being, well, pretty well informed on this complex topic.
Sounds like a plan.
Okay, so let's set the scene. Imagine stepping into a physics lab, maybe mid-20th century. After years of simplifying things, protons, neutrons, electrons, suddenly these high-energy particle accelerators start spitting out this bewildering array of new particles.
Oh, yeah. It really was like opening Pandora's box.
It's called a particle zoo, right? Utterly chaotic. You've got dozens of new things, hadrons, mesons, baryons, all supposedly elementary. But how could so many particles truly be fundamental? It felt like physics was hitting a wall.
Exactly. It wasn't just a growing list. It was a genuine crisis, a crisis in our understanding of what elementary even meant. New particles kept popping up, pions, kaons, various lambda and sigma baryons, and the sheer number just defied any simple explanation.
It's just too many.
Way too many. And to make things even more confusing, some of them, like the kaons, behaved very strangely. They were produced really easily by the strong force, but then they decayed on timescales much, much longer than you'd expect.
Slower than they should have.
Much slower. This led physicists like Murray Gell-Mann and Kazuhiko Nishijima to propose a new conserved quantum number they called strangeness, which, helped categorize them, but it really only deepened the puzzle. What was really going on underneath? There was this urgent, almost desperate need for some kind of underlying order.
So, okay, chaos reigns. What was the next big idea? How did they finally start, imposing some order on this zoo?
Well, that brings us to Murray Gell-Mann and also Yuval in 1961. They proposed something truly elegant. It was called the Eightfold Way.
The Eightfold Way, okay.
And what was so profound about it was, well, it was far more than just a clever filing system. It was a mathematical blueprint, a kind of hidden symmetry. It didn't just organize the known particles, it actually predicted new ones. It revealed this deeper, simpler order underneath all that chaos.
Like Mendeleev's periodic table, but for particles.
That's a great analogy, yeah. It hinted at what must be there. And it was built on this powerful mathematical symmetry, SU3 specifically, which was actually an extension of Werner Heisenberg's earlier SU2 symmetry that described protons and neutrons.
Isospin.
Exactly, isospin. So this SU3 symmetry, its success was undeniable. It almost seemed to demand the existence of even more fundamental constituents making up these patterns.
Okay, so the Eightfold Way brings order, but it sounds like it also maybe created a new mystery. If these patterns were so real, what was actually causing them?
Exactly. You've hit the nail on the head. That profound question led directly to what was, at the time, a truly revolutionary and, frankly, quite heretical idea.
Okay. The Court hypothesis, 1964.
That's the one.
Right. Here's where it gets really interesting, I think. Murray Gell-Mann, who famously plucked the name Quarks from James Joyce.
Finnegan's Wake, yeah. 3 quarks for Muster Mark.
Right. And independently, George Zweig, a postdoc at CERN who called them ACEs. They proposed that these elementary hadrons, well, they weren't elementary at all, they were composites, built from just a handful of even more fundamental things.
A radical idea.
And here's the kicker, right? To make this work, these proposed quarks had to have fractional electric charges, plus 2/3, minus 1/3 of the basic charge unit. Now, this just flew directly in the face of decades of physics, like Millikan's oil drop experiment, which showed charge always came in whole number multiples. That must have caused quite a stir.
Oh, absolutely. A huge stir. That's precisely why Gell-Mann was so cautious initially. He called them mathematical entities, maybe not physically real. And Zweig's paper, which was much more direct about them being real particles, was considered so outlandish by the senior folks at CERN that it actually never got published in a journal.
Wow, really? Just too weird.
Too weird, too challenging to the established picture. You can imagine the uproar. It questioned everything they thought they knew about electric charge. Yet, despite all that skepticism, the model worked. I mean, it brilliantly classified all the known particles, and crucially, it even predicted the existence of a new baryon, the omega minus.
And that was found.
It was found shortly after, yeah, exactly as predicted. So for nearly a decade, quarks existed in this strange limbo. A brilliant mathematical success, but a physical impossibility in the minds of many. It desperately needed some kind of experimental proof.
Okay, so this static quark model, it's a great start. Explains the patterns.
Yeah.
But it was incomplete, right? It didn't explain how these quarks actually stuck together.
Yeah.
And it quickly ran into a major problem with quantum mechanics.
That's right.
Specifically, particles like the delta plus plus baryon, that was thought to be 3-up quarks. But how could 3 identical fermions, all with their spins aligned, exist in the same quantum state? That seemed to violate the Pauli exclusion principle.
Fundamental principle, yeah. And that's where the ingenious solution of color charge came in, proposed around 1965. Now, this new quantum number, it has absolutely nothing to do with visible light. The names red, green, and blue, they're just whimsical labels.
Convenient names.
Exactly. The idea was that each of the 6 quark flavors also comes in 3 different colors, and antiquarks have anticolors. So the 3 up quarks in the delta plus plus could exist together because each carried a different color, one red, one green, one blue. Problem solved.
Okay, so it gave them a way to be different, even if they were the same flavor and spin.
Precisely. It solved the Pauli paradox. But crucially, this color charge wasn't just some, clever workaround. It was eventually revealed to be the fundamental charge of the strong interaction itself. This laid the groundwork for quantum chromodynamics, or QCD. That's the full quantum field theory of the strong force, developed in the early 1970s.
So if color charge is this new fundamental charge, like electric charge,
Yeah.
does it have its own force carrier particle, like the photon for electromagnetism?
Exactly. And those are the gluons. Gluons are the force carriers for the strong force in QCD, but they're truly unique beasts.
How so?
Well, unlike photons, which are electrically neutral, gluons themselves carry color charge. For instance, a gluon might be, say, red anti-blue. And this is hugely important. It means gluons don't just interact with quarks, they also interact with each other.
Ah, okay. So photons don't interact with other photons directly, but gluons interact with gluons. That sounds like it would make things complicated.
It makes things very interesting. That capacity for gluon self-interaction is the defining feature of QCD, and it gives rise to its 2 most profound and at first glance seemingly contradictory behaviors.
Okay, let's unpack this. What are these 2 pillars of QCD?
The first is color confinement. This is the reason why we never ever see individual quarks or gluons floating around freely in isolation. They are permanently confined within color-neutral composite particles.
Permanently stuck inside.
Permanently. Think of it like trying to pull a quark and an antiquark apart. With electromagnetism, the force gets weaker as you pull them further away. Not so with the strong force. Because the gluons interact with each other, the field between the quarks gets squeezed into this incredibly energetic flux tube, or string.
Like a rubber band, but much stronger.
Kind of, but the energy in this tube actually increases linearly with distance. It gets stronger the further you pull. So before you could ever pull them infinitely far apart, so much energy builds up in that tube that it becomes energetically cheaper to create a new quark-antiquark pair right out of the vacuum. EMCICA. Yeah. That flux tube essentially snaps, and instead of getting isolated quarks, you just get 2 new color-neutral hadrons. This is why we only ever find white or color-neutral combinations in nature. Baryons, made of 3 quarks, 1 red, 1 green, 1 blue, or mesons, made of a quark and an antiquark, like red and anti-red.
Okay, that explains why we can't just knock a quark out of a proton. What's the other pillar? You said it seems contradictory.
Right. The second pillar, which seems like the opposite but is really the other side of the same gluon interaction coin, is asymptotic freedom.
Asymptotic freedom sounds liberating.
In a way, yes. It means that while the strong force is incredibly powerful at the distances inside a proton holding quarks together, it paradoxically becomes remarkably weak at very short distances or equivalently at very high energies.
Weaker up close. That's the opposite of magnetism or gravity.
Exactly the opposite. Think about electromagnetism. Virtual particles tend to screen an electric charge, making it appear weaker from far away. With gluons, their self-interaction produces an anti-screening effect. It's like the gluons spread out the quark's color charge, making it appear weaker the closer you get.
That's completely counterintuitive.
Totally. But it's absolutely crucial. This phenomenon was discovered by David Gross, Frank Wilczek, and David Pulitzer, and it won them the Nobel Prize in 2004 because it was essential for making QCD a theory you could actually calculate things with.
So what does this all mean? How do confinement and freedom fit together?
They are two sides of the same coin, both emerging from gluon self-interactions. Confinement explains why quarks are bound forever inside hadrons. Asymptotic freedom explains why, if you hit a proton really hard with a high-energy particle, the quarks inside behave almost as if they were free point-like particles. It resolved the big paradox from those early scattering experiments. You could see these point-like things inside, but you can never actually knock one out on its own.
Incredible. These forces are just mind-bending. Okay, let's shift focus a bit from the forces to the quarks themselves. What are they actually like? What defines them individually?
That's a great question. So the standard model tells us there are 6 distinct types or flavors of quarks. We have up, down, charm, strange, top, and bottom.
The 6 flavors.
Right. And they're organized into 3 generations. The first generation is up and down. The second is charm and strange. And the third is top and bottom. And this 3-generation structure, interestingly, mirrors the structure we see in the leptons, the electron, muon, tau, and their neutrinos.
And across these generations, there's this, well, truly staggering difference in mass, isn't there?
Oh, it really is staggering. The first generation quarks, the up and down that make up protons and neutrons, are tiny, just a few MeV in mass. That's mega electron volts divided by the speed of light squared, our unit for particle mass.
Very light.
Very light. But then you jump to the third generation and you get the pop quark. It's the most massive elementary particle we've ever discovered. It weighs in at around 172,000 MeV.
172,000. Compared to just a few for the up and down.
Exactly. To put that in perspective, it's roughly 172 times the mass of a proton. And incredibly, it's comparable to the mass of an entire gold nucleus. Imagine a single fundamental particle being that heavy.
That's unbelievable. And this mass difference has consequences, right, for stability?
Huge consequences. This mass hierarchy directly dictates stability. The heavier quarks, charm, strange, top, and bottom are all inherently unstable. They rapidly decay through the weak interaction into the lighter first-generation quarks. That's why all the stable matter that makes up you, me, the planets, the stars, everything we see is composed exclusively of up and down quarks, plus electrons, of course.
So when we talk about quark mass, it seems like it's not quite as simple as, say, an electron's mass. I've heard physicists talk about current quark mass and constituent quark mass. What's the difference there?
Yeah, that's a really crucial distinction, and it ties back to QCD and confinement. The current quark mass is what you might think of as the intrinsic naked mass of a quark. It's the value that comes directly from its interaction with the Higgs field. And for the up and down quarks, it's incredibly small, like we said, about 2.3 MeV for the up and maybe 4.8 MeV for the down. Tiny.
Okay, that's the Higgs mass. What's the constituent mass then?
The constituent quark mass is more like an effective mass. It's the mass a quark seems to have when it's bound inside a hadron. It includes not just its small current mass, but also the enormous energy contribution from the surrounding gluon field and the sea of virtual quark-antiquark pairs that are constantly flickering in and out of existence within that hadron due to confinement.
So it includes the energy of its environment.
Exactly. And here's the truly mind-blowing aha moment. Let's take a proton. It's made of 2 up quarks and 1 down quark, right?
Yep.
If you add up their current masses, 2 times 2.3 plus 4.8, you get less than 10 MeV. Maybe around 9.4 MeV.
Oh, less than 10.
But the measured mass of a proton is about 938 MeV.
Whoa, wait. Where does all the rest come from? That's almost all of it.
Precisely. The intrinsic Higgs mass of the quarks themselves contributes only about 1% to the proton's total mass. The other 99% of the mass of all the protons and neutrons that make up basically all the visible matter in the universe doesn't come from the Higgs boson at all. It's an emergent property of QCD. It arises predominantly from the kinetic energy and the binding energy of that incredibly powerful gluon field holding the quarks together. It's EMC caught in action, turning pure energy into mass.
That is profound. So most of what we think of as everyday mass isn't from the fundamental particle masses given by the Higgs, but from the energy of the strong force holding things together.
Wow, okay.
It really changes your perspective on where mass comes from.
Absolutely. So beyond mass and flavor, what other fundamental properties define these quarks? Well, they're defined by several other key intrinsic quantum numbers. We've already mentioned their fractional electric charge. Plus 23e for up, charm, top, next 13e for down, strange, bottom. Radical idea initially, but it works perfectly to ensure all the composite hadrons end up with integer charges, like +1 aim for the proton, 0 for the neutron.
It makes the math work out.
Exactly. Then there's color charge, red, green, or blue, which we discussed as the source of the strong force. All quarks are spin 12 particles, which makes them fermions. That means they obey the Pauli exclusion principle, which color charge helps satisfy.
Right, the spin.
They also possess a baryon number of +13. This is a conserved quantity, and it explains why baryons, like protons and neutrons, are always made of 3 quarks, total baryon number +1, while mesons are made of a quark and an antiquark, total baryon number +13 plus -13 equals 0.
Neat. Keeps track of the quarks.
Precisely. And finally, they have various flavor quantum numbers, things like weak isospin, strangeness, charm, bottomness, and topness. These essentially define their specific flavor type and govern how they participate in the weak interactions, the ones responsible for decay. You can actually see a nice detailed catalog of all these properties in Table 1 in our source material if you want the full breakdown.
Great. So now we know their individual properties. How do they actually, engage with the universe? It seems pretty remarkable that quarks are the only elementary particles known to participate in all 4 fundamental forces.
It really highlights their unique position, doesn't it? They're central players. Let's quickly run through each interaction. First, obviously, the strong interaction, mediated by gluons. We've covered that it's dominant, binding quarks into protons and neutrons, holding atomic nuclei together.
The strongest force, hence the name.
Right. Then there's the electromagnetic interaction. Since quarks carry electric charge, they interact by exchanging photons. This is responsible for holding atoms together, chemistry, light, all that. Then we have the weak interaction. This one's mediated by the heavy W and Z bosons. It's incredibly important because it's the only force that can change a quark's flavor. This allows heavier, unstable quarks to decay into lighter, more stable ones. It's crucial for processes like nuclear fusion in stars and radioactivity.
The agent of transformation, as we called it earlier.
Exactly. And finally, there's gravity. Quarks have mass, even if most of it is binding energy, so they are subject to gravity. But honestly, at the subatomic scale we're talking about, gravity's effects are completely and utterly negligible. It's something like 138 times weaker than the strong force. Just irrelevant down here.
Mind-bogglingly weak in comparison. Okay, so the strong force, through color confinement, dictates how quarks combine to these color-neutral hadrons. You mentioned this process, hadronization. What are the main families of these composite particles again?
Right. Hadronization is the process where quarks and gluons, which might be produced in a high-energy collision, bundle themselves up into the color-neutral particles we actually observe. And there are 2 main families. First, baryons. These are made of 3 quarks. To be color-neutral, or white, they have to have 1 quark of each color, say 1 red, 1 green, and 1 blue.
Like the proton and neutron.
Exactly. Those are the most famous ones. Since quarks are spin 12 fermions, baryons always end up with half-integer spin, like 12, 32, etc., which means they are also fermions. And as we said, they have a baryon number of +1.
Okay, 3 quarks. What's the other family?
The other family is mesons. These are composed of 1 quark and 1 antiquark. Here, color neutrality is achieved because the antiquark carries the anticolor of the quark.
Yeah.
For instance, a red quark bound to an anti-red antiquark makes a color-neutral state.
Color and anti-color cancel out.
Precisely. Mesons have integer spin, 0, 1, 2, which makes them bosons, and they have a baryon number of 0, +13 from the quark, never 13 from the antiquark. Common examples you might have heard of are pions and kaons.
Right. And it's pretty neat how you can figure out the properties of any specific hadron, like its electric charge or its strangeness, just by adding up the quantum numbers of the quarks inside it, like subatomic arithmetic.
It absolutely is. That quark arithmetic works remarkably well for predicting the basic properties. For example, the proton, Ud, has charge +23 + 23 13 equals +1. The neutron has +23 13 13 equals 0. It's very elegant.
Simple addition.
At that level, yes. Though it's important to remember that while this picture of just the valence quarks, the main Ud or Ud, etc., is really useful, a real hadron is a much more dynamic and complex object. Inside, there's also this roiling sea of virtual quark-antiquark pairs and gluons constantly popping in and out of existence, contributing to the overall properties.
So this simple picture is useful, but the reality is messier.
As always in quantum physics. But sticking with the main idea, the weak interaction is truly the key agent of transformation here. It's unique in its ability to change quark flavor. That's what allows unstable particles to decay. Think about a free neutron decaying into a proton, that famous beta decay.
Right, a neutron doesn't live forever on its own.
Exactly. At its heart, what's happening inside is that one of the neutron's down quarks, UD, transforms into an up quark, make a HUD, a proton, emitting a W- boson in the process. That W- then immediately decays into an electron and an electron antineutrino. That flavor change, D to U, is fundamental to how matter changes and evolves in the universe. And the probabilities for these different quark flavor changes, like how likely a strange quark is to decay into an up quark versus down quark, are precisely described by something called the Kabibo-Kobayashi-Maskawa matrix, or CKM matrix for short.
The CKM matrix sounds important.
It is. In fact, Makoto Kobayashi and Toshihide Maskawa realized way back in 1973 that explaining a subtle asymmetry observed between matter and antimatter, called CP violation, which is crucial for understanding why our universe is dominated by matter, could only be accommodated within this framework if there were at least 3 generations of quarks.
Wow, so they predicted the 3rd generation before it was found.
They did. It was a brilliant theoretical insight based on the CKM matrix needing complex numbers to allow for CP violation, which required 3 generations. Their prediction was later spectacularly confirmed by the discovery of the bottom quark in 1977, and finally the top quark in 1995, solidifying a 3-generation structure, the Standard Model, and earning them the Nobel Prize. By the way, Table 2 in your sources lists the quark compositions of many common hadrons, like the proton, neutron, the omega-, even things like the JP-Xi meson, so you can really see this quark arithmetic in action.
Okay, so after all this brilliant theory, the Eightfold Way, quarks, QCD, the CKM matrix, how did we actually go from this, radical hypothesis of fractionally charged things hidden inside protons to concrete, undeniable experimental proof? How do we see them?
Well, see is maybe metaphorical here, but the decisive evidence came from a series of experiments known as deep inelastic scattering, or DIS. These were carried out at the Stanford Linear Accelerator Center, SLAC, in the late 1960s and early 1970s, led by Jerome Friedman, Henry Kendall, and Richard Taylor.
Deep inelastic scattering. Okay, what did they do?
It was actually analogous in spirit to Rutherford's famous gold foil experiment that discovered the atomic nucleus almost 60 years earlier. They fired very high-energy electrons, like tiny probes, at protons and neutrons.
Okay, shooting electrons at protons.
Right. Now, if the proton was just sort of a diffuse, uniform blob of charge, you'd expect the electrons mostly to pass right through or maybe get deflected by small angles.
Like shooting bullets through fog.
Exactly, but that's not what they saw. The results were really striking. A significant number of electrons bounced back at very large angles, some almost straight back. It was as if they had hit something small, hard, and point-like inside the proton.
Like hitting tiny ball bearings inside the fog.
Precisely. And that was it. This was the first direct physical evidence for quarks. Richard Feynman, who was developing the theoretical framework to understand these results, called these point-like constituents partons. And the way the electrons scattered, the patterns they observed, perfectly matched the predictions for scattering off point-like particles carrying the fractional electric charges that Gell-Mann and Zweig had proposed.
So the scattering patterns revealed the fractional charges.
They did. The data strongly supported the +23 and -13 charges. For this groundbreaking work, Friedman, Kendall, and Taylor were awarded the Nobel Prize in Physics in 1990.
Well-deserved, sounds like. Was there other evidence, too?
Oh, yes, absolutely. Other evidence quickly accumulated. For example, experiments colliding electrons and their antimatter counterparts, positrons, produced hadrons. The rate at which hadrons were produced compared to pairs of muons, which are like heavy electrons, strongly supported the idea that each quark flavor came in 3 distinct colors. The numbers just worked out perfectly if you included that factor of 3 for color.
The color charge showing up in production rates.
Exactly. And also the observation of jets in particle collisions. When quarks or gluons are produced with high energy, they can't exist freely due to confinement. Instead, they fragment into a collimated spray, or jet, of ordinary hadrons moving roughly in the original direction of the quark or gluon. Seeing these jets is now considered a routine, almost visual confirmation of the underlying quarks and gluons, showing hadronization in action.
So we've come a really long way. From a confusing particle zoo to actually seeing evidence of quarks and jets. What's next? Where is quark research heading now? What are physicists trying to figure out on the frontiers?
Well, we're definitely not done with quarks. We're actually on the cusp of some potentially incredible new discoveries. One major front is at the Large Hadron Collider at CERN. It's currently undergoing a major upgrade to become the High Luminosity LHC, or HL-LHC. That's scheduled to start running after 2030.
High luminosity, meaning more collisions.
A lot more collisions. The plan is for it to be a veritable top quark factory. It aims to produce billions, literally billions, of top quark-antiquark pairs over its lifetime.
Billions. Why so much focus on the top quark? Just because it's heavy?
Precisely because it's so incredibly massive. Its large mass makes it unique. It decays so quickly it doesn't even have time to form hadrons. And many theories of physics beyond the standard model predict that new particles or forces might interact preferentially with the top quark because of its large mass. So, by studying the top quark with unprecedented precision, physicists hope it might be our most direct window into finding that new physics.
Here's where it gets really interesting again then. Looking for clues in the heaviest quark.
Exactly. The huge datasets from the HL-LHC will allow physicists to search for incredibly rare processes involving the top quark. Things like, for instance, flavor-changing neutral currents processes, where a top quark might decay directly into, say, a charm quark and a Z boson. These are almost completely forbidden, practically non-existent in the standard model.
So if they see that.
If they see even a hint of that happening more often than expected, it would be a smoking gun. It would be like finding a hidden door pointing towards a whole new universe of particles or forces beyond what we currently know.
Very exciting. And there's also another big project, a completely new machine being built in the US, right? The Electron-Ion Collider, or EIC.
Yes, the EIC at Brookhaven National Laboratory. This is going to be a truly unique state-of-the-art facility. It represents a real paradigm shift in how we study the structure of matter.
A paradigm shift.
Right.
How so? What will it do differently?
Well, for decades, our picture of the proton has been largely one-dimensional, understanding how momentum is distributed along the direction of motion. The EIC is designed to be the first machine capable of colliding high-energy beams of spin-polarized electrons with beams of spin-polarized protons and heavy ions. This combination will allow us to create the first-ever three-dimensional CT scans of the proton and the nucleus.
3D pictures inside a proton.
Essentially, yes. Mapping out not just the momentum, but also the precise spatial distribution of quarks and gluons inside. It's like going from a blurry X-ray to a detailed 3D image. This unprecedented view will help us tackle some major outstanding puzzles.
Like what?
One big one is the proton spin puzzle. We know protons have spin 12, but when you add up the spins of the three main valence quarks, you only get about 30% of the total spin. Where does the rest come from? The EIC is designed to finally measure all the contributions from the quark spins, yes, but also from the gluon spins, and crucially, from the orbital angular momentum of both quarks and gluons swirling around inside the proton.
So finding the missing spin. What else?
It will also allow us to probe the behavior of gluons at extremely high densities, searching for a predicted state of matter called the color glass condensate, where gluons might actually saturate. And fundamentally, the EIC aims to provide unprecedented insight into how the gluon field actually confines quarks, and as we discussed, how it generates nearly all the visible mass in our universe through binding energy. It's really about understanding the dynamics of QCD in a whole new way. It marks an evolution from just inferring existence to taking static pictures to actually mapping the dynamic 3D structure of how matter is built.
It sounds like these next-generation experiments are poised to really transform our understanding. But while quarks represent this monumental triumph in physics explaining so much, they also seem to point toward the limits of our current understanding, don't they? Despite all these discoveries, they've unveiled a new set of profound mysteries. Could you tell us about the flavor problem, for instance? What makes it so perplexing?
Indeed, the standard model, despite its incredible success, leaves some really big questions unanswered, and many of them revolve around quarks and their properties. The flavor problem really has two main baffling aspects. The first is the hierarchy problem concerning the quark masses.
The huge range of masses we talked about earlier.
Exactly. That seemingly arbitrary and absolutely enormous range. The top quark is over 300,000 times more massive than the electron and nearly 100,000 times heavier than the up quark. In the standard model, these masses just come from how strongly each quark happens to couple to the Higgs field. But the model gives us absolutely no explanation for why these coupling values are what they are, why these specific numbers. This vast, unexplained spread feels unnatural to many physicists. It's a kind of fine-tuning puzzle that strongly suggests there must be some deeper physics at play, perhaps a more fundamental theory that actually dictates these values, rather than them just being arbitrary inputs.
So why these masses? That's one part. What's the other part of the flavor problem?
The other part is the generation problem. Why exactly 3 generations of quarks and leptons? The second and third generations seem to be almost exact copies or replicas of the first generation, just much, much heavier. Why does nature repeat this structure? And why only 3 times?
Is there any reason to think there might be a fourth generation we haven't found?
Well, precision measurements of how the Z boson decays very strongly constrain the number of light neutrino species to be exactly 3. Since each generation seems to come with its own neutrino, this makes a fourth generation with a light neutrino highly improbable. And direct searches at the LHC have looked for heavier fourth-generation quarks, but they haven't found any, setting very high lower limits on their possible mass well into the TeV range, probably too heavy to have affected Z decay. So while not absolutely ruled out, a fourth generation looks incredibly unlikely. But that just deepens the mystery. Why specifically 3? It remains one of the most fundamental open questions in physics. We just don't know.
3 generations, specific masses. It feels like we're missing something fundamental. And this, I guess, leads us inevitably to the ultimate question that always seems to linger in particle physics. Are quarks truly elementary? Could there be something even smaller inside?
That's the million-dollar question, isn't it? Or maybe the billion-dollar question now. The whole history of physics, from atoms to nuclei to protons and neutrons, has been one of continuously peeling back layers of structure, finding that things we thought were fundamental were actually composite. So it's only natural to wonder if quarks and leptons might themselves be composite, made of even more fundamental constituents. These hypothetical building blocks are sometimes called preons.
Preons. So quarks made of preons. What would be the appeal of that?
Well, the appeal of preon models is that they try to simplify things again. They aim to reduce the standard model's current particle zoo, with its dozens of parameters, quarks, leptons, bosons, down to maybe just a handful of truly fundamental preons and a new force binding them. If successful, such a theory could potentially explain things like the generation structure. Maybe the generations correspond to different excited states of the preon system, and even derive fundamental parameters like quark masses and charges from a simpler underlying theory instead of just measuring them and plugging them in.
That sounds very attractive theoretically. Are there problems with the idea?
Oh, yes. There are significant theoretical hurdles. The biggest one is often called the mass paradox. Think about trying to confine these hypothetical preons inside something as small as a quark, which experiments tell us must be incredibly tiny, if not point-like. The rules of quantum mechanics, specifically the Heisenberg uncertainty principle, tell us that the more tightly you confine something, the larger the uncertainty in its momentum must be, which translates into immense kinetic energy.
So tiny box means huge energy.
Huge energy. This energy itself would contribute an enormous amount of mass to the quark, far, far more than the measured masses, especially for the light quarks. So if quarks were made of preons, you'd need some incredibly powerful, new, and frankly quite contrived hyperforce between the preons that provides a huge negative binding energy to perfectly cancel out almost all of that enormous kinetic energy. It feels a bit like adding an ad hoc solution just to make the numbers work out.
Doesn't sound very elegant. What about experiments? Can we test this?
Physicists are definitely looking. At the LHC, for example, they search for any signs of quark substructure. If quarks weren't point-like but had internal structure, you might expect to see deviations from the standard model predictions in very high-energy collisions, perhaps revealing new contact interactions between the preons inside colliding quarks. So far, absolutely no such deviations have been found. This pushes the compositeness scale, the energy scale at which you might see preons, up to incredibly high energies, likely tens of TeV or even higher, well beyond the direct reach of our current experiments. So for now, quarks still look point-like as far as we can tell.
It really highlights this duality, doesn't it? The quark is, on one hand, this monumental triumph. It brought order to the particle zoo, explained the structure of protons and neutrons, and gave rise to quantum chromodynamics, which is this stunningly successful theory of the strongest force in nature.
Absolutely. A pillar of the standard model.
But on the other hand, the quark itself, its very existence and properties, has become a source of some of the most profound and currently unanswered questions in 21st century particle physics. Their specific masses, why they fall into that hierarchy, their precise mixing angles described by the CKM matrix, why there are exactly 3 generations. These are all just parameters we measure and plug into the standard model. They're inserted by hand, as physicists say, not derived from any deeper principle within the model itself.
That's exactly right. The standard model describes how quarks behave with incredible accuracy, but it doesn't explain why they have the fundamental properties they do.
And even something as basic sounding as proving mathematically with full analytic rigor, the QCD actually does confine quarks permanently. That's still an unsolved problem. It's actually one of the Clay Mathematics Institute's Millennium Prize problems.
That's right. Proving confinement and the existence of a mass gap in QCD is still a major challenge for theoretical physics and mathematics. We know it happens, we can simulate it on supercomputers, but a complete pencil and paper proof remains elusive.
So, the quark isn't really the end of the story, is it? It seems more like a crucial signpost, pointing towards a deeper reality we haven't grasped yet.
I think that's the perfect way to put it. The ongoing experimental programs like the HL-LHC and the future facilities like the EIC, they aren't just about cataloging quark properties with ever-increasing precision, although that's important. They're really designed to use quarks, especially the heavy ones like top and bottom and the way they interact via gluons, as exquisitely sensitive tools. Tools to probe for those subtle cracks, those tiny deviations from the standard model's predictions that could finally reveal the next, more fundamental theory, perhaps, one that will finally explain the quark itself, its mass, its flavor, why there are 3 generations.
So the quest continues.
The quest definitely continues. The study of quarks has truly evolved. It started as bringing order to chaos, then became a discovery of fundamental constituents, and now it's really a profound quest for the origins of the fundamental rules that govern our entire universe. Quarks are at the very heart of that quest today.
So here's a final thought for you, our listener, to maybe mull over. What if this very concept of fundamental isn't a destination we reach, but something we'll always be chasing, like an infinitely nested set of Russian dolls? And maybe the quark is just our current, clearest window into that potentially endless possibility. Just consider how something so incredibly tiny, so seemingly abstract, holds such massive implications for our understanding of reality, generating almost all the mass we see and still holding on to its deepest secrets.